The National Electrical Code prevails over the plans regarding ground rod conductor size. The National Electrical Code is a minimum standard. Anything that meets or exceeds the National Electrical Code requirements is acceptable. In this case, the National Electrical Code clearly states that a ground rod conductor shall not be required to be larger than number 6. The purpose of the grounding conductor is to provide a low impedance path for fault currents to flow back to the source. The size of the conductor is determined by the potential fault current and the expected length of the run. While oversizing the conductor may provide some additional protection, it is not required by the National Electrical Code and may not be necessary in most cases. The main disadvantage of oversizing the conductor is increased cost and complexity. The inspector's role is to ensure that the electrical installation meets the minimum requirements of the National Electrical Code. This includes verifying that the grounding conductor is properly sized and installed. However, the inspector is not responsible for enforcing design enhancements that are not required by the National Electrical Code. If the plans call for a larger conductor than what is required by the National Electrical Code, it is generally advisable to follow the plans. While the National Electrical Code is a minimum standard, it is important to consider the specific conditions of the installation and provide additional protection where necessary. However, it is also important to understand that oversizing the conductor is not always necessary and may not be the most cost-effective solution. To elaborate further, let's consider the role of the National Electrical Code. The National Electrical Code, or NEC, serves as a baseline for electrical safety. It outlines the minimum acceptable standards for electrical installations to protect people and property from hazards. It is not intended to be a design manual or a comprehensive guide for every possible electrical scenario. This is why the NEC is considered a minimum standard. Engineers and designers often go above and beyond the NEC requirements to address specific project needs, environmental conditions, or client preferences. Now let's examine the purpose of the grounding electrode conductor, or GEC. The grounding electrode conductor connects the electrical system to the grounding electrode, which is typically a ground rod, ground plate, or underground metallic water pipe. Its primary function is to provide a low impedance path for fault currents to return to the source, which helps to quickly trip a circuit breaker or fuse and clear the fault. The NEC specifies the minimum size of a grounding electrode conductor based on the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor for various service entrance conductor sizes. However, it's important to note that for connections to ground rods, ground plates, and concrete encased electrodes, the grounding electrode conductor is not required to be larger than number 6 copper or number 4 aluminum. This is because the impedance of the grounding electrode itself limits the amount of fault current that can flow. Now let's talk about oversizing conductors. While it might seem like oversizing the grounding electrode conductor would provide additional protection, it's generally not necessary and may not provide any significant benefit. The impedance of the grounding electrode is the limiting factor, not the size of the conductor. In fact, oversizing the conductor can sometimes create problems. For example, a larger conductor is more difficult to work with and may require larger connectors and fittings. It can also increase the cost of the installation. It is also critical to understand the inspector's role. The electrical inspector is responsible for enforcing the NEC and ensuring that electrical installations meet the minimum safety requirements. The inspector will verify that the grounding electrode conductor is properly sized, installed, and connected. However, the inspector is not responsible for enforcing design enhancements or requirements that go beyond the NEC. If the plans call for a larger grounding electrode conductor than what is required by the NEC, the inspector will typically accept it as long as it meets all other applicable requirements. Now let's consider a scenario. Suppose the plans specify a 4/0 copper grounding electrode conductor for a connection to a ground rod. According to the NEC, a number 6 copper conductor would be sufficient. In this case, the contractor has a few options. Firstly, the contractor could install the 4/0 copper conductor as specified in the plans. This would meet the requirements of both the plans and the NEC. Secondly, the contractor could install a number 6 copper conductor, which would meet the minimum requirements of the NEC. However, the contractor would need to obtain approval from the engineer or designer who created the plans. Thirdly, the contractor could submit a change order to the engineer or designer, requesting that the plans be revised to specify a number 6 copper conductor. This would require the engineer or designer to evaluate the situation and determine if a number 6 copper conductor is acceptable. Ultimately, the decision of whether to install the 4/0 copper conductor or the number 6 copper conductor will depend on a number of factors, including the specific requirements of the project, the preferences of the client, and the cost of the materials and labor. It's important to carefully consider all of these factors before making a decision. In conclusion, the NEC prevails as the minimum standard, but project specifications can exceed it. Grounding electrode conductor sizing is governed by NEC Table 250.66, with a maximum requirement of number 6 copper for ground rod connections. Oversizing offers limited benefit due to grounding electrode impedance. Inspectors enforce NEC minimums, not design enhancements. Adherence to plans exceeding NEC should be considered, but cost-effectiveness should also be taken into account. It is important to consult with qualified professionals for project-specific considerations. To further expand on the topic of grounding electrode conductors and their application, it's beneficial to delve into some related concepts and considerations. Firstly, let's address the concept of impedance versus resistance. While both terms describe opposition to current flow, impedance is a more comprehensive term that includes both resistance and reactance. Reactance is the opposition to current flow caused by capacitance and inductance in alternating current circuits. In grounding systems, impedance is the critical factor because fault currents are typically alternating current. The impedance of the grounding electrode, which includes the resistance of the soil and the reactance of the grounding electrode itself, limits the amount of fault current that can flow. This is why oversizing the grounding electrode conductor has limited benefit. Secondly, let's consider the different types of grounding electrodes. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, concrete encased electrodes, and underground metallic water pipes. The type of grounding electrode used will depend on the specific site conditions and the requirements of the project. Ground rods are commonly used because they are relatively inexpensive and easy to install. Ground plates are often used in areas with high soil resistivity. Concrete encased electrodes, also known as U for grounds, are typically used in new construction. Underground metallic water pipes are sometimes used as grounding electrodes, but they must be supplemented with another type of grounding electrode. Thirdly, it's important to understand the requirements for grounding electrode installation. The NEC specifies the requirements for grounding electrode installation in Article 250. These requirements include the depth and spacing of ground rods, the size and material of ground plates, and the bonding of different grounding electrodes together. Proper grounding electrode installation is essential for ensuring the effectiveness of the grounding system. Fourthly, let's discuss the importance of bonding. Bonding is the process of connecting different metallic parts of the electrical system together to create a low impedance path for fault currents. Bonding is essential for preventing voltage differences between different metallic parts, which can be a shock hazard. The NEC specifies the requirements for bonding in Article 250. These requirements include the size and material of bonding conductors, the methods of making bonding connections, and the bonding of different types of equipment. Fifthly, it is helpful to consider the role of ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electric shock. They work by monitoring the current flowing in the circuit and tripping the circuit if there is a ground fault. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. While GFCIs provide important protection against electric shock, they do not eliminate the need for proper grounding. Grounding is still necessary to provide a low impedance path for fault currents and to help trip circuit breakers or fuses. Sixthly, it is important to understand the requirements for surge protection. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other events. SPD are typically installed at the service entrance and at sensitive electronic equipment. While SPD can provide valuable protection against voltage surges, they do not eliminate the need for proper grounding. Grounding is still necessary to provide a low impedance path for surge currents and to help divert the surge energy away from sensitive equipment. Seventhly, consider the impact of soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Soil with high resistivity is more difficult to ground than soil with low resistivity. The NEC specifies the requirements for grounding in areas with high soil resistivity. These requirements may include the use of multiple ground rods, ground plates, or chemical ground rods. Eighthly, one must understand the testing and maintenance of grounding systems. Grounding systems should be tested periodically to ensure that they are functioning properly. The most common test is a ground resistance test, which measures the resistance of the grounding electrode to earth. Grounding systems should also be visually inspected for any signs of damage or corrosion. Any damaged or corroded components should be replaced immediately. Ninthly, the coordination between grounding and bonding. Grounding and bonding are two distinct but related concepts. Grounding provides a path for fault currents to return to the source, while bonding connects different metallic parts of the electrical system together to create a low impedance path for fault currents. Proper coordination between grounding and bonding is essential for ensuring the safety and effectiveness of the electrical system. Lastly, the design considerations for specific applications. The design of the grounding system will depend on the specific application. For example, a grounding system for a hospital will have different requirements than a grounding system for a residential building. The design of the grounding system should take into account the type of equipment being used, the environmental conditions, and the potential for fault currents. By considering these related concepts and considerations, one can gain a more comprehensive understanding of grounding electrode conductors and their application. It's essential to consult with qualified professionals for specific project requirements and to ensure compliance with all applicable codes and standards. Furthermore, focusing on grounding electrode conductor materials is also important. The most common materials used for grounding electrode conductors are copper and aluminum. Copper is a better conductor of electricity than aluminum, but it is also more expensive. Aluminum is lighter and less expensive than copper, but it is more susceptible to corrosion. The NEC specifies the requirements for the size and material of grounding electrode conductors in Article 250. The size of the conductor is determined by the size of the service entrance conductors. The material of the conductor must be suitable for the environment in which it is installed. Copper conductors are typically used in corrosive environments, while aluminum conductors are typically used in dry environments. Now let's consider grounding electrode conductor connections. The connections between the grounding electrode conductor and the grounding electrode must be mechanically strong and electrically conductive. The NEC specifies the requirements for grounding electrode conductor connections in Article 250. The connections must be made using approved methods such as exothermic welding, listed connectors, or bolted connections. The connections must be protected from corrosion. Then there are grounding electrode conductor protection requirements. Grounding electrode conductors must be protected from physical damage. The NEC specifies the requirements for grounding electrode conductor protection in Article 250. The conductors must be installed in conduit or raceway if they are exposed to physical damage. The conductors must be protected from corrosion if they are installed in a corrosive environment. The location of the grounding electrode conductor is important as well. The grounding electrode conductor should be as short and direct as possible. The NEC specifies the requirements for grounding electrode conductor location in Article 250. The conductor should be run in a straight line from the service equipment to the grounding electrode. The conductor should not be run through any unnecessary bends or loops. The grounding electrode conductor identification is important to recognize as well. Grounding electrode conductors must be identified. The NEC specifies the requirements for grounding electrode conductor identification in Article 250. The conductors must be identified by a tag or label that indicates that they are grounding electrode conductors. The tags or labels must be permanently affixed to the conductors. The function of the grounding electrode conductor is to provide a low impedance path for fault currents to return to the source. The grounding electrode conductor is connected to the grounding electrode, which is typically a ground rod, ground plate, or underground metallic water pipe. The grounding electrode provides a connection to the earth, which helps to dissipate fault currents. It is also useful to discuss the differences between system grounding and equipment grounding. System grounding is the grounding of the electrical system neutral point. Equipment grounding is the grounding of the non-current carrying metal parts of electrical equipment. System grounding is intended to limit voltage to ground and provide a path for fault currents to return to the source. Equipment grounding is intended to protect people from electric shock by providing a lower impedance path for fault currents to return to the source. Furthermore, it is good to discuss the benefits of proper grounding. Proper grounding provides many benefits, including protection from electric shock, reduction of fire hazards, improved equipment performance, and reduced noise. It is important to ensure that electrical systems are properly grounded to protect people and property from electrical hazards. To re-emphasize a point, it is important to consult with qualified professionals for specific project requirements and to ensure compliance with all applicable codes and standards. This will provide a comprehensive view of grounding electrode conductors and their proper application.